Hello everyone. Today we will study normal approximation for binomial and Poisson distribution. Let's first of all discuss the normal approximation for binomial distribution. Consider a set S that contains only two elements, success and failure. When an element is chosen from the set, S, let P be the chance of getting success. Let P be the chance of getting success. Then we know that the chance of getting failure is 1 minus P. Next, then the random variable X represent the number of obtained success. Then the random variable X represents the number of obtained success. Then X is either 0 or 1. We are either getting 1 success or 0 success. So suppose X is either 0 or 1. Then X has a Bernoulli distribution. Since we only try once, X has a Bernoulli distribution. Since we only do the experiment once, X has a Bernoulli distribution with perimeter P. We only choose one element once, and the chance of getting success is P. X has a Bernoulli distribution. Next, let the random variable Y equal to S1 plus S2 plus Xn. Where each xi is identical to x. Then S1, S2, Sn, they are independent and identically distributed. Random variables. By the central limit theorem. By the central limit theorem we learned last class, As n approaches to infinity, y tends to a normal distribution. As n tends to infinity, as n approaches to infinity, y tends to a normal distribution. As n approaches to infinity, y tends to a normal distribution. Now, what does y represent here? Here, y equal to s1 plus s2 plus sn. And s1, s2, sn, they all represent the number of obtained success when choosing element from the set. Since y equal to s1 plus s2 plus sn, y equal to the total number of obtained success when choosing n elements from the set with replacement. And the chance for every trial, the chance of getting success is the same, O equal to p. Then we can say y has a binomial distribution. Y has a binomial distribution. So we can say y has a binomial distribution. With perimeter n and p. Since y represents the total number of obtained success when choosing n element from the set with replacement, and the chance of getting success for every trial is the same, they all equal to p. Then I can say y has a binomial distribution. So here we can see that as n tends to infinity, y tends to a normal distribution. So we can say that for a binomial distribution, with parameters, for a binomial distribution with parameters n and p, as n tends to infinity, as n approaches to infinity, the binomial distribution tends to a normal distribution. By the central limit theorem. So let's make a conclusion. For the normal approximation, for binomial distribution, then the random variable x let x be a random variable with x has a binomial distribution n and p. There's no difference, I call a random variable x or y. There's no difference, I call a random variable x or y. So let x be a random variable with x has a binomial distribution with parameters n and p. Then as n approaches to infinity, x tends to a normal distribution. with its special value of x in the earlier section, we know that for binomial distribution, its special value of x is n times p, and the variance of x is n times p times 1 minus p. So since x has a binomial distribution, its special value of x is n times p. And variance of x is n times p times 1 minus p. That's the normal approximation for binomial distribution. So here we can see that as n is sufficiently large, we can use the normal distribution to approximate a binomial distribution. But for n, how big is called sufficiently large? How big is called sufficiently large? Note, in general, when n times p is greater or equal to 5, and n times 1 minus p is also greater or equal to 5, when n times p and n times 1 minus p, they are both greater or equal to 5, then the normal approximation is a good approximation. The normal approximation for the binomial distribution is good. It's a good approximation. When n times p and n times 1 minus p, if they are both greater than 5, then we can say that the normal approximation is a good approximation. Next, let me introduce normal approximation for Poisson distribution. Let's first of all consider the following. Under some fixed conditions, assume event occurs continuously. Assume events occur continuously. And the occurrence of the events are independent. And the occurrence of the events are independent. Also, at every time period, or at every place with a fixed length, at every time period or every place with a fixed length or fixed area, the average number of occurrence of the event is known. The average number of the occurrence of the events is known. Denoted by Lambda Flowing. every time period with a fixed length, the average number of the occurrence of the events is known, denoted by lambda prime. Usually we use lambda, but here we'll use lambda for something else. Let me call lambda prime. So in a time period with a fixed length, every time period with a fixed length, suppose that's the fixed length of the time period, the average number of the occurrence of the event is known to be lambda prime. Assume the event will occur this many times in this fixed time interval. Next, we'll divide this time interval into k equal subintervals. Next, we'll divide this time interval into k equal subintervals. We divide this time interval into k equal subintervals. Next, we divide this fixed time period into k equal subintervals. Suppose that's the first interval called I1, that's the second interval called I2, that's the third interval called I3, and that's the kth interval called I sub k. We divide this time period into k subintervals, k equal subintervals. Then the average number of an occurrence of the events in each subinterval I sub I is lambda prime over k. If I divide this time period into k equal subintervals, then the average number of occurrence of the event in each subinterval will be lambda prime over k. Since there are k subintervals, I take lambda prime divided by k. The average number of the occurrence of the event in each subinterval I is lambda prime over k. Here, k is a constant. K is an integer constant. K is a constant integer. And also, we try to make each time interval, we try to make each subinterval to be relatively small. So we make k larger than lambda prime. We try to make each subinterval relatively small. So I make k greater than equal to lambda prime. We try to make each subinterval relatively small. Next, then the random variables. Si represent the actual number of an occurrence of the events in the interval I sub I, where I equal to 1, 2, 3 until infinity. So that's I equal to 1, I equal to 2, I equal to 3, I equal to k. Continue, we have that's a fixed time interval. Continue, we have I sub k plus 1, I sub k plus 2 until infinity. Then each xi they are independent random variables. Because the occurrence of an event are independent. Because the occurrence of an event are independent. So Si, they are independent random variables. And they all has Poisson distribution with lambda equal to lambda prime over k. They all have Poisson distributions, and on each interval, the average number of occurrence of an event is lambda prime over k. They all have Poisson distribution with lambda equal to lambda prime over k. Hence they are all identical. Hence Si, they are all identical. Hence Si's they are independent and identically distributed. Independent and identically distributed random variables. Since they are independent and they all have Poisson distribution with the same lambda, so they're identical. They are called independent, identically distributed random variables. Next, let the random variable y equal to S1 plus S2 plus Sn. Let the random variable y equal to S1 plus S2 plus Sn. S1 plus S2 plus Sn, say that's the nth interval. Then, by the central limit theorem, as n approaches to infinity, here we cannot use k. We cannot use S1 plus S2 plus Sk because k is a constant. We cannot take a limit for constant, so we must use Xn. As n approaches to infinity, y tends to a normal distribution. So by central limit theorem, as n approaches infinity, y tends to a normal distribution. Here, be very careful for one thing. Y equal to S1 plus S2 plus Sn. The last term here, it must be x sub n. It cannot be x sub k. If we put s sub k here, then when applying the central limit theorem, we must take a limit as k approaches infinity. If we take a limit as k approaches infinity, k cannot be a constant. K must be a variable. If k is a variable, then every subinterval I sub I depends on k. If I sub I depends on k, then the random variable Si, they all depends on k. If every random variable Si depends on k, they must be dependent random variables. If they all depends on k, they must be dependent random variables. So they are not independent. We cannot apply the central limit theorem. Therefore, it must be, the last term here must be x sub n. And then we can take a limit as n approaches infinity. Then, by central limit theorem, as n approaches infinity, y tends to a normal distribution. Next, let's try to recognize what kind of probability distribution y is. Next, let's try to recognize what kind of probability distribution y is. Here, since S1, S2, Sn, they are all Poisson distributions. S1, S2, Sn, they are all Poisson distributions. They are all Poisson random variables. And y is the sum of all Poisson random variables. Y must also be a random variable. Since y is the sum of Poisson random variables, y must also be a Poisson random variable. Y is also a Poisson random variable. Since y is the sum of n Poisson random variables, y is also a Poisson random variable. Since y is a Poisson random variable, what's its perimeter lambda? What's its lambda? In an earlier section, we know that for any Poisson random variable with perimeter lambda, its expected value is always the same as lambda. For any Poisson random variable with a perimeter lambda, its expected value is always lambda. So, since y is a Poisson random variable, its expected value must be the same as lambda. So lambda here, lambda of y, equal to the expected value of y. Now, how do we find the expected value of y? We know that y equal to S1 plus S2 plus Sn. So expected value of y is the expected value of S1 plus S2 plus Sn. That can be rewritten as expected value of S1 plus expected value of S2 plus expected value of x sub n. Since S1, S2, Sn, they all have Poisson distribution, so their expected value must be the same as their lambda. Since S1, S2, Sn, they all have Poisson distribution, so their expected value must be the same as their lambda. So expected value of S1 is lambda prime over k. Expected value of S2 is also lambda prime over k. Expected value of Sn is also lambda prime over k. Here, from S1, S2 to Sn, there are n terms. From S1, S2 to Sn, there are n terms. And these terms, they are all identical. For the sum of n identical terms, their sum is 1 of the term times n. I take 1 of the term times n. That's the sum. And since y also has Poisson distribution, its special value of y is the same as lambda of y. Since y also has Poisson distribution, its special value of y is lambda of y. So lambda of y equal to lambda prime over k times n. So for the random variable y, is lambda equal to lambda prime over k times n. For y, it's lambda equal to lambda prime over k times n. Since lambda prime is a positive constant, k is also a positive constant, then I can say lambda and n, they are proportional to each other. Lambda and n, they are proportional to each other. Here, lambda and n, they are proportional to each other. Which means the larger lambda, the larger n, and the larger n, the larger lambda. As n approaches infinity, lambda approaches infinity. And as lambda approaches infinity, n approaches infinity. So here we can say that for a Poisson random variable, for a Poisson distribution with perimeter lambda, as lambda approaches infinity, since lambda and n they are proportional, as lambda approaches infinity, n also approaches infinity, then the Poisson distribution tends to a normal distribution. As lambda approaches infinity, the Poisson distribution tends to a normal distribution by the central limit theorem. So as lambda approaches infinity, since lambda and n they are proportional to each other, n also approaches infinity. So y tends to a normal distribution. So the Poisson distribution tends to a normal distribution by the central limit theorem. So let's make a conclusion here. For the normal distribution, normal approximation for Poisson distribution, let x, there's no difference I call this x or y. Let x be a random variable. With x has a Poisson distribution with perimeter lambda. let x be a random variable with x has a Poisson distribution with perimeter lambda. Then, as lambda approaches to infinity, x tends to a normal distribution. With its special value of x equal to lambda. According to an earlier section, we know that for any Poisson random variable with perimeter lambda, its special value is always lambda. And the variance of x is also lambda. Variance of x is also lambda. So that means when lambda is sufficiently large, the Poisson distribution approaches to a normal distribution. But how big is called sufficiently large? How big of lambda should be? How big should lambda be? Note, in general, when lambda is greater than 20, it's considered sufficiently big enough, sufficiently large. When lambda is greater than 20, it's considered sufficiently large. So when lambda is greater or equal to 20, then the normal approximation for the Poisson distribution is a good approximation. It's considered a good approximation. When lambda is greater than 20, it's considered sufficiently large. The normal approximation for the Poisson distribution is a good approximation. Next, let's look at some examples about using normal approximation for binomial and Poisson distributions. First example, when a coin is tossed 1,000 times, find each of the following probabilities. Part A, what's the probability of getting exactly 500 heads? Part B, what's the probability that the number of obtained heads is more than 520? Part C, what's the probability that the number of obtained heads is between 470 and 490 inclusive? Let's set down a problem first. When we toss a coin, we either get head or tail. In this problem, we're looking for number of heads. So consider head represents success, tail represents failure. And when we toss a coin for every trial, the probability of getting heads is the same. When we toss a coin 1,000 times, we can consider there 1,000 trials. And the chance for every trial of getting head is the same. So we can consider this is a binomial distribution. Let's set up a problem first. Then the random variable x represent the number of obtained heads. The number of obtained heads. In this 1,000 toss. then X has a binomial distribution. With n equal to 1,000, what's P? When we toss a coin, the chance of getting head is a half, so P is half. X has a binomial distribution. With n equal to 1,000, P equal to half. According to an earlier section, we know that for any binomial random variables with parameters n and p, its expected value is always n times p, and its variance is always n times p times 1 minus p. Here, x is a binomial random variable with n equal to 1,000, p equal to half. So its expected value is always n times p, which is 1,000 times half. 1,000 times half is 500. Variance of x is always n times p times 1 minus p. Here n is 1,000, p is a half. 1 minus p is 1 minus half, that's another half. 1,000 times half, that's 250. So mu of x is the same as expected value of x equal to 500. And sigma of x is square root of the variance of x, which is square root of 250. That's the setup. Now answer the question. Part A. What's the probability of getting exactly 400 heads? What's the probability of getting exactly 400 heads? This is a binomial distribution. X is a binomial distribution. If we solve it directly, we're looking for probability that x equal to 500. The formula for binomial distribution is n choose x, p to the power of x times 1 minus p to the power of n minus x. That's the formula for binomial distribution. Here we plug in 1,000. If we plug in 1,000 for n, 500 for x, then plug in half for p, plug in 500 for x, 1 minus p, that's another half. n minus x, n is 1,000, x is 500. 1,000 minus 500 is another 500. If we try to solve this in the calculator, it won't work. Because this number, 1,000 choose 500, that's a huge number. Calculator won't work for such large numbers. So it doesn't work in the calculator. If we try to solve it directly, it doesn't work in the calculator. Since it doesn't work in the calculator, we try to find a probability using a normal approximation. We try to use a normal approximation for this binomial distribution. Before we use normal approximation for binomial distribution, let's verify two things. We must verify that n times p must be greater or equal to 5. And n times 1 minus p must be greater or equal to 5. Here, n times p is 500. In this problem, n times p is 500, which is greater than 5. N times 1 minus p, n is 1,000, 1 minus p, 1 minus half, and that's another half. 1,000 times half, that's 500. Since both n times p and n times 1 minus p, they are both greater than 5, that means if I use a normal approximation, it will be a good approximation. Here we know that when n is sufficiently large, this binomial random variable x tends to have a normal distribution. Since x has a normal distribution, we can convert x to z, the standard normal distribution. Then use a table of the standard normal CDF to find the probabilities. Let's convert x to z first. The formula for conversion is z equal to s minus mu over sigma. g equal to s minus mu over sigma. That's a formula for conversion. So we take 500 minus mu. Mu is also 500 over sigma. Sigma is radical 250. Here, 500 minus 500 over radical 250 is 0. What's the probability that g equal to 0? Since g is the standard normal distribution, g is a continuous random variable. Probability for any continuous random variable equal to a constant is always 0. Probability for any continuous random variable equal to a constant is always 0. Because for this probability, we take integral from a to a, f of x dx. Integral from a to a is always 0. So for any continuous random variable, probability that s equal to a is always 0. Since g is a continuous random variable, this probability is 0. Does it make sense? Does this answer make sense? We know that when we toss 1,000 coins, it's possible to have 400 heads. When we toss 1,000 coins, it's possible to have 400. It's possible to have 400 heads. So this probability is clearly not 0. So that's wrong. If we solve it like this, that's wrong. Now, how can we use normal approximation to find the probability here? Here, since x has a binomial distribution, we know that for each x in the support, there are some probabilities. For example, when x equals to 500, suppose that's its probability. I draw a bar representing its probability. The height of the bar represents its probability. The height of the bar represents probability. Suppose that's a probability when s equals to 499. And suppose that's a probability when s equals to 498. And so on. On the other side, suppose that's a probability when s equals to 501. We also the height represent probabilities. Suppose that's a probability when s equals to 502. And so on. We know that when n is sufficiently large, this binomial distribution tends to have a normal distribution. When n is sufficiently large, this binomial distribution tends to have a normal distribution. In order to find a probability using normal distribution, we try to find the probability under the curve over this bar. In order to approximate the probability, we try to find the probability under the curve over this bar for s equals to 500. We try to find the probability under the curve over this bar. Now for this probability here, we try to find area under the curve between these 2 points. What's these 2 points? This point is the midpoint of 499 and 500. This point is the midpoint of 499 and 500. So the left end point here is 499.5. The right end point is a point between 500 and 501. So that's the midpoint between 500 and 501, which is 500.1. So if we try to use normal distribution to approximate this binomial distribution, we must find the area under the curve from 499.5 and 500.5. We need to find area under the curve between 499.5 and 500.5. So if I use normal distribution to approximate binomial distribution, I need to find the area under the curve between 499.5 and 500.5. This is called the half-unit continuity correction. This is called a half-unit continuity correction. making probability that x equal to 500 equal to probability that x between 499.5 and 400.5. This is called the half-unit continuity correction. Usually, just call this continuity correction. Now, since x has a normal distribution, I can convert x to the standard normal distribution. The formula for conversion, again, is g equal to s minus mu over sigma. (499.5) minus mu. Mu is 500. Sigma is radical 250. So take 499.5 minus mu over radical 250. Then the other side is 500.5 minus mu over sigma. Sigma is radical 250. Then its calculator. Round the answer to 2 decimal places. Here I get negative 0.03 on the left side. On the right side, I get positive 0.03. Then, in order to find the probability using the table of the standard normal CDF, I must rewrite the probability in the form of probability that g is less or equal to some constant, or probability that g is less than constant. They both equal to phi of g. They both equal to phi of the constant. This probability can be rewritten as probability that g is less than 0.03 minus probability that g is less or equal to negative 0.03, which is phi of 0.03 minus phi of negative 0.03. Then use the table. Phi of 0.03. Phi of 0.03 is 0.51197. 0.51197. Phi of negative 0.03. Negative 0.03 is here. It's 0.48803. 0.48803. Next calculator. When I subtract, this is 51197. Use calculator. When I subtract, I get 0.02394. In general, for the final answer, we round to 4 decimal places. That's about 0.0239. Next, let me write down the half-unit continuity correction in detail. In general, when we use normal approximation, for any discrete random variables, to find the probability that s equal to a, we need to use half-unit continuity correction. We need to apply half-unit continuity correction. Sometimes it's just called continuity correction. which means probability that S is equal to A. If I use normal approximation, that's probability that S is between A minus half and A plus half. When we use normal approximation to approximate S probability S equal to A, I need to take a probability for S is between A minus half and A plus half. In this example here, when we try to find probability that S equal to 500 using normal approximation, I need to find probability that S is between 500 minus half and 500 plus half. This is called the half unit continuity correction. Sometimes it's also called the continuity correction. Next, let's look at part B. What's the probability that the number of obtained heads is more than 520? So part B, we're looking for probability that X is more than 520. Since binomial distribution is a discrete random variable, we need to apply continuity correction. If we apply continuity correction, what do we get? If we apply continuity correction, what do we get? Let's draw some bars represent these numbers. Let's draw some bars first. For example, 520 is here. For binomial distribution, there are some probabilities for all x in the support. Suppose there's a probability when s is 520. The height represents probability. The height of the bar represents probabilities. 521 is here. 522 is here. 519 is here. We are looking for probability that x is more than 520. That means s could be 521, s could be 522, and so on. We try to find probabilities for this area, for this part here. If I use normal approximation, we try to find area under the curve over these bars. So here, left endpoint, the left endpoint is 520.5. The left endpoint here is 520.5, and go all the way to infinity. So if I apply half unit continuity correction, that's the probability that s is greater than 520.5. When we use normal approximation to approximate binomial distribution for any discrete random variables, we need to apply half unit continuity correction. That's what we get here. Next, we need to convert x to z. Since x tends to have a normal distribution, we can convert x to z to the standard normal distribution. The formula for conversion is x minus mu over sigma. So here we use 520.5 minus mu. Mu is 500 over sigma. Sigma is 250. Sigma is not equal to 250. Then use calculator. Round the answer to 2 decimal place. Here, if I round the answer to 2 decimal place, I get 1.30. Since we try to use the table of the standard normal CDF to find probability, I try to divide the probability in the form of probability that z less or equal to some constant, or probability that z less than some constant. They both equal to phi of z. They both equal to phi of the constant. Here we have probability that z is greater than 1.30. I can use the complement. That's 1 minus probability that z is greater than z is less or equal to 130. That's 1 minus phi of 1.30. Therefore, phi of 1.30, I can find it in the table. Phi of 1.30 is 0.90320. Next calculator, I get 0.0968. That's part B. Part C. What's the probability that the number of obtained heads is between 470 and 490 inclusive? What's the probability that the number of obtained heads is between 470 and 490 inclusive? Part C, we're looking for probability that S is between 470 and 490 inclusive. That means we include the endpoint. That's the probability that S is between 470 and 490. Next, since X is a discrete random variable, we need to apply continuity correction. Since X is binomial distribution, which is a discrete random variable, we need to apply continuity correction. If I apply continuity correction, what do we get here? Let's draw some bars. Suppose that's 469. That's a probability for S is 469. That's 470. That's 471, and so on. That's 489. That's 490. That's 491. We're looking for probability that S is between 470 and 490 inclusively. Inclusively, that means we include 470 and 490. Since X tends to have a normal distribution, we're looking for probability under the curve over its bars. We're looking for probability under the curve over its bars. For this area here, the left endpoint is the point between 469 and 470. So the left endpoint is 469.5. The right endpoint is a point between 490 and 491. That's 490.5. So after continuity correction, we're looking for probability that S is between 469.5 and 490.5. That's what we get after continuity correction. Next, we need to convert X to Z to the standard normal distribution. The formula for conversion is X Z equal to S minus mu over sigma. Mu is 500. Sigma is radical 250. Mu is 490. Sigma is mu is 500. Sigma is radical 250. After conversion, it's Z. We have the standard normal distribution here. Next, find the probability. Use calculator, round each number to two decimal place. Use calculator, round each number to 2 decimal place. Here I get negative 1.93. For the number on the right side, I get negative 0.60. Use calculator, round to 2 decimal places. That's what I get here. Next, in order to use the table of the standard normal CDF, I try to run a probability in these two forms. Probability that Z less than some number or probability z less than or equal to some number, or probability z less than some number. They both equal to phi of the constant. So this can be rewritten as probability that z is less than negative 0.60 minus probability that z is less than or equal to negative 1.93. That's phi of negative 0.60 minus phi of negative 1.93. Phi of negative 0.60 in the table. Negative 0.6 is here. Negative 0.60 is here. 0.27425. 0.27425. Phi of negative 1.93. Phi of 1.93. Negative 1.93 is here. That's 0.02680. 0.02680. Then I use my calculator. The answer is 0.24745. In general, we want to answer to 4 decimal places. That's 0.2475. That's the probability that the number of obtained heads is between 470 and 490 inclusive. Next example, when a die is rolled 240 times, find each of the following probabilities. Part A, what's the probability that number 1 comes up exactly 30 times? Part B, what's the probability that number 1 comes up fewer than 35 times? Part C, what's the probability that number 1 comes up between 40 and 50 times inclusive? Let's set down the problem first. In this problem, we are looking for number of obtained ones. When we know a die, we can consider number 1 as a success and numbers other than 1 as failures. Every time when we know a die, the chance of getting 1 is the same, which is 1 over 6. And we are rolling a die 240 times. We can consider this is a binomial distribution. So let's set down a problem. Let the random variable x represent the number of obtained ones. Let the random variable x represent the number of obtained ones. When a die is rolled 240 times. Then x has a binomial distribution. With n equal to 240. Since we know the die 240 times, n is 240, and p is 1 over 6. When we know a die, the chance of getting number 1 is 1 over 6. So x is a binomial distribution with n equal to 240 and p equal to 1 over 6. According to an earlier section, we know that since x has a binomial distribution, its special value of x is always n times p. According to an earlier section, we know that its special value of x is always n times p, which is 240 times 1 over 6, which is 40. And the variance of x is always n times p times 1 minus p, which is 240 times 1 over 6 times 1 minus 1 over 6 is 5 over 6. That's 100 over 3. That's the expected value of x and the variance of x. Then we know that mu of x is the same as expected value of x, which is 40. And sigma of x is square root of the variance of x. which is square root of 100 over 3. It's mu and sigma of x. Now that's the setup. Based on the setup, let's answer the question here. Part A. What's the probability that number 1 comes up exactly 30 times? So part A, we're looking for probability that s equal to exactly 30. How do we find the probability that s equal to 30? If we use the probability function of x directly, f of 30 is what? Since x is a binomial random variable with n equal to 240, p equal to 1 over 6, its probability function is n choose x, 240 choose x, p to the power of x times 1 minus p to the power of m minus x is 240 minus x, where x is integers from 1 to 240. For f of 30, we plug in 30 directly. We plug in 30 to f of x. Plug in 30 for each x. I get 240 to 30 times 1 over 6 to the power of 30 times 5 over 6 to the power of 240 minus 30 is 210. Then use calculator, round to 4 decimal places. I get 0.0154. That's the exact answer. That's the answer without using approximation. That's the exact answer. That's the exact probability where s is 30. That's the exact probability. That's the exact probability where s is 30. Now, if I try to use normal approximation, what do we get? If I try to use normal approximation here, let's verify two things: n times p and n times 1 minus p. If they are both greater than 5, it will be a good approximation. Let's verify two things: n times p and n times 1 minus p. N times p is 240 times 1 over 6, which is 40. That's greater than 5. N times 1 minus p is 240 times 1 minus p. P is 1 over 6. 1 minus 1 over 6 is 5 over 6. That's 200, which is also greater than 5. That means if I use normal approximation, it will be a good approximation. So let's use normal approximation here. Since x is a discrete random variable, when we apply normal approximation, we need to apply half unit continuity correction. Since x is a discrete random variable, when we use normal approximation, we need to apply half unit continuity correction. So apply half unit continuity correction. For probability that s equal to 30, I go down by half unit. 30 minus half is 29.5. 30 go up by half unit is 30.5. Since here n is sufficiently large, by central limit theorem, x tend to a normal distribution. Since x has an approximate normal distribution, I can convert x to z, convert x to the standard normal distribution. Then use the table of the standard normal CDF to find the probability. Let's first of all convert x to z. Convert x to the standard normal distribution first. The formula for conversion is z equal to x minus mu over sigma. Here we use 29.5 minus mu. Here mu is 40, sigma is radical 100 over 3. 29.5 minus mu over sigma. On the other side, we use 30.5 minus mu over sigma. Then calculate these two expressions. Use your calculator. Round to 2 decimal places. Here I use my calculator. I get negative 1.82 and negative 1.65. Next, in order to use the table of the standard normal CDF, we need to rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of the number. Phi of the number here. So this probability here can be rewritten as probability that z is less than negative 1.65 minus probability that z is less or equal to negative 1.82. That's phi of negative 1.65 minus phi of negative 1.82. Then it's a table. For phi of negative 1.65, negative 1.65, I get 0.4947. 0.04947. For phi of negative 1.82, negative 1.8 is here, 2 is here. I get 0.03438. 0.03438. Then subtract. I get 0.01509. In general, for the final answer, we round to 2 decimal places, 4 decimal places. I get 0.0151. 0.0151. That's an approximate probability. This is not an actual answer. That's an approximate probability. Here we can see that this approximate answer is very, very close to the actual answer. So we can see that when n is sufficiently large, this normal approximation is a good approximation. So that's an answer to part A. Part B. What's the probability that number 1 comes up fewer than 35 times? Part B. What's the probability that number 1 comes up fewer than 35 times? So for part B, we're looking for probability that x is less than 35. If we try to solve it directly using the probability function, we need to compute f of 0 plus f of 1 plus f of 2 plus plus f of 34. We must compute each term individually and add it up, find the sum. That's a probability. But here, from f of 0 to f of 34, there are 35 terms. If we try to compute all 35 terms, it may be too much work. So for easier way, we can try to use normal approximation. Here, x is a binomial random variable. And both n times p and n times 1 minus p, they are greater than 5. That means if I use normal approximation, it will be a good approximation. So let's use normal approximation here. Since x is a discrete random variable, when we use normal approximation, we need to apply half-unit continuity correction. Since x is a discrete random variable, when we use normal approximation, we need to apply half-unit continuity correction. So apply half-unit continuity correction. In order to apply half-unit continuity correction, let's draw some bars first. Let's draw some bars around 35 first. Suppose that's the probability for x equal to 33. Suppose this high represents the probability for x equal to 33. Suppose the height of this bar represents the probability when x equal to 34. Suppose the height of the bar represents the probability when x equal to 35. Suppose the height of the bar represents the probability when x equal to 36. These bars together, all these bars together, that's called a probability histogram. All these bars together, from 0 to 240. This bar, all these bars together is called a probability histogram. The bars for all x in the support together is called a probability histogram of this random variable x. For probability that x is less than 35, we're looking for x is 34, 33, and so on. And we know that when n is sufficiently large, this random variable x tend to a normal distribution by central limit theorem. When n is sufficiently large, this binomial random variable x has the approximate normal distribution. When n is sufficiently large, x tend to a normal distribution. And when we apply normal approximation, we try to approximate the area under the curve over these bars. We try to approximate the area under the curve over these bars. So here, for these bars, the endpoint here is the midpoint between 34 and 35. The midpoint between 34 and 35 is 34.5. So that's an endpoint. The endpoint here is 34.5. So by central limit theorem, this x, when n is sufficiently large, this x tend to a normal distribution. And after apply half unit continuity correction, x is less than 34.5. After we apply half unit continuity correction, x is less than 34.5. Since x has the approximate normal distribution, we can convert x to z first. We can convert x to the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. So convert x to z. The formula for conversion is z equal to x minus mu over sigma. Here, mu is 40. Sigma is square root of 100 over 3. So we get 34.5 minus 40 over square root of 100 over 3. Then calculate this expression using calculator. Round to 2 decimal places. That's probability that z is less than negative 0.95. Probability that z is less than negative 0.95. That's phi of negative 0.95. Use the table. Find phi of negative 0.95. Negative 0.9 is here. Phi is here. The intersection here is 0.17106. 0.17106. 0.17106. In general, for the final answer, round to 4 decimal places. I get 0.1711. That's the probability that the number of obtained number ones, the number of obtained ones is less than 35. That's the answer to part B. Now for part C, what's the probability that number 1 comes up between 40 and 50 times exclusive? What's the probability that number 1 comes up between 40 and 50 times exclusive? So for part C, we're looking for probability that S is between 40 and 50 exclusive. If we try to solve it directly, we can use the probability function of X. Find f of 41 plus f of 42 plus f of 49. From f of 41 to f of 49, there are nine terms. We must compute each term individually and then add them up. If we solve it this way, it's doable, but maybe too much work. So for a simpler way, we can try to use normal approximation. For a simpler way, we can try to use normal approximation. Here, both n times p and n times 1 minus p are greater than 5. That means if we use normal approximation, it will be a good approximation. So let's use normal approximation here. Since x is a discrete random variable, when we apply normal approximation, when we use normal approximation, we need to apply half unit continuity correction. Since x is a discrete random variable, when we use normal approximation, we need to apply half unit continuity correction. In order to apply half unit continuity correction, let's draw a probability histogram around 40 and 50s first. Let's draw a probability histogram around 40 and 50s first. Suppose that's a probability where s is 39. Suppose that's a probability where s is 40. Suppose that's a probability where s is 41. Suppose that's a probability where s is 42. Continue. Suppose that's a probability where s is 48. Suppose that's a probability where s is 49. Suppose that's a probability where s is 50. Suppose that's a probability where s is 51. We're looking for probability that s is between 40 and 50. That means we don't include 40, we don't include 50. Start from 41, 42, go all the way to 48, 49. We know that when n is sufficiently large, the binomial random variable x tend to a normal distribution by central limit theorem. X tend to a normal distribution by central limit theorem. When we use normal approximation, we try to approximate the area under the curve over these bars. We try to approximate the area under the curve over these bars. For these bars here, the left endpoint is the endpoint between is the midpoint between 40 and 41. The left endpoint is the midpoint between 40 and 41, which is 40.5. That's the left endpoint. The right endpoint is the midpoint between 49 and 50. That's 49.5. So if we use normal approximation, x is between 40.5 and 49.5. We know that when n is sufficiently large, this x tend to a normal distribution. Then we can convert x to the standard normal distribution and then use the table of the standard normal CDF to find the probabilities. The formula for conversion is g equal to x minus mu over sigma. Let's convert x to g first. The formula for conversion is g equal to x minus mu over sigma. Here, mu is 40. Sigma is square root of 100 over 3. So I have 40.5 minus mu over sigma x, I convert x to z. And for 49.5, I do 49.5 minus mu over sigma. Then calculate this expression using calculator. Round to 2 decimal places. For the first expression, I use my calculator. I get 0.09. And for this number here, I use my calculator. I get 1.65. In order to use the table of the standard normal CDF to find the probability, I need to rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of the number. They both equal to phi of the number. They both equal to phi of this number here. So this probability can be rewritten as probability that z is less than 1.65 minus probability that z is less or equal to 0.09. That's phi of 1.65 minus phi of 0.09. Then it's a table of the standard normal CDF. For phi of 1.65, 1.6 is here, phi is here. 1.65 is 0.95053. 0.95053. For phi of 0.09, in the table, 0.0 is here, 9 is here. I get 0.53586. I get 0.53586. Then subtract. I get 0.41467. In general, for the final answer, round the answer to 4 decimal places. In general, for the final answer, round to 4 decimal places. I get 0.4147. That's the probability that the number of obtained ones is between 40 and 50 exclusive. That's an answer to part C. Next example. In a barber shop, customers visit an average rate of 4 customers per hour. Assume the barber shop opens 10 hours a day. Part A. In a given day, what's the probability that exactly 35 customers visit? Part B. In a given day, what's the probability that at least 45 customers visit? Part C. In a given day, what's the probability that the number of visiting customers is between 30 and 50 exclusive? Let's set out a problem first. We know that customers visit at an average rate of 4 customers per hour in a fixed time interval. If we know the average number of occurrence of events, we can use Poisson distribution. So, let the random variable x represent the number of visiting customers in a given day. Let x represent number of visiting customers in a given day. Then x has a Poisson distribution. What's lambda here? What's lambda here? Visiting customers is 4 customers per hour. 4 customers per hour. Then how many customers in 10 hours? We know the barber shop open 10 hours a day. Customer visits in 4 hours, which is at a rate of 4 customers per hour. How many customers will visit in 10 hours? In the same rate. Here we can cross multiply. Lambda equal to 40. Since customers visit at a rate of 4 customers per hour, it will be 40 customers in 10 hours. So X has a Poisson distribution with lambda equal to 40. Then in the earlier section, we know that for any random variables with Poisson distribution, its special value of X is always lambda. Variance of X is also lambda. So here, its special value of X is lambda, which is 40. Variance of X is also lambda, which is also 40. Next, find mu of X and sigma of X. Mu of X is always the same as its special value of X, which is 40. Sigma of X is square root of the variance of X, which is square root of 40. Now, let's answer the question. Part A. In a given day, what's the probability that exactly 35 customers visit? Part A. What's the probability that exactly 35 customers visit? So in part A, we're looking for probability that S equal to 35. If we try to solve it directly using Poisson distribution, what do we get? If we try to solve it directly using Poisson distribution, the formula for Poisson distribution is e raised to negative lambda times lambda raised to power of x over x factorial. Here, lambda is 40. If I plug in, I get e raised to negative 40 over lambda to the power of x. Here, x is 35 over 35 factorial. Here, if I use my calculator and round the answer to 4 decimal place, I get 0.0485. That's the exact probability. Now, if I try to use a normal approximation, what do I get? That's the exact probability. That's the answer without approximation. That's the exact probability. Now, if I try to use normal approximation for these probabilities, what do I get? First of all, this random variable x has a Poisson distribution. When we use normal approximation for Poisson distribution, we need to make sure lambda is greater than 20. When lambda is greater than 20, you will have a good approximation. Here, in this example, lambda is 40. For this random variable x, lambda is 40, which is greater than 20. So if I use normal approximation, it will be a good approximation here. So when lambda is sufficiently large, this x, by central limit theorem, this random variable x tend to have a normal approximation. If I use normal approximation for s equal to 35, I need to apply half unique continuity correction. I need to apply half unique continuity correction. If I apply half unique continuity correction for probability that s equal to 35, I need to find probability that s is between 35 minus 0.5 and 35 plus 0.5. 35 minus 0.5 is 34.5, and 35 plus 0.5 is 35.5. Since this x tend to have a normal distribution, I can convert x to the standard normal distribution, z. Let's convert x to z, the standard normal distribution. The formula for conversion is z equal to x minus mu over sigma. So here I take 34.5 minus mu. Here mu is 40 over sigma. Sigma here is radical 40. Here I convert x to z. And then for 35.5 I use 35.5 minus mu over sigma. Next, I use my calculator. Round the answer to 2 decimal places. I get probability that z is between negative 0.87 and negative 0.71. Since we try to find probabilities using the table of the standard normal CDF, I need to rewrite a probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of z. They both equal to phi of z. So this probability here can be rewritten as probability that z is less than negative 0.71 minus probability that z is less than negative 0.87. This is phi of negative 0.71, and this is phi of negative 0.87. Next, use the table of the standard normal CDF to find the probabilities. For phi of 0.71, phi of negative 0.71, negative 0.7 is here, 1 is here. I get 0.23885, 0.23885. Next, use the table to find phi of negative 0.87. Negative 0.8 is here, 7 is here. Negative 0.87 is 0.19215, 0.19215. That's phi of negative 0.87. Then I subtract. I get 0.0467. That's an approximate probability for x equal to 35. This is an approximate answer. This is an approximate answer using normal approximation. That's an approximate probability using normal approximation. We can see that this answer is very, very close to the actual probability. This answer is very close to the exact probability. So when lambda is greater than 20, it has a very good approximation. Part B, in a given day, what's the probability that at least 45 customers visit? At least 45 customers means 45 or more customers. Let's set down a problem first. For part B, we're looking for probability that x is greater than or equal to 45. If we try to solve it directly, we must compute f of 45 plus f of 46 plus f of 47 plus until infinity. Since there are infinitely many terms, if we try to compute in this way, it's almost impossible since there are infinitely many terms. How about the complement? If we use the complement, probability that x is greater or equal to 45 can be written as 1 minus probability that x is less than 45, which is 1 minus f of 0 plus f of 1 plus f of 2 plus plus f of 44. If we try to solve it in this way, we must compute f of 0, f of 1, f of 2 until f of 44 individually. There are 45 terms. From f of 0 to f of 44, there are 45 terms. We must compute all 45 terms individually, then add them up. Use 1 minus the sum to find the probability. It's doable, but if we solve it in this way, it may be too much work. It's doable, but it may be too much work. In order to make the problem a little easier, we can try to use normal approximation. Here, x is a Poisson random variable with lambda equal to 40. We know that if lambda is more than 20, when we use normal approximation, it will be a good approximation. So let's apply. Let's use normal approximation. Since x is a Poisson random variable, it's discrete. When we use normal approximation, we must apply half-unit continuity correction. Since x is a discrete random variable, we must apply half-unit continuity correction. In order to apply half-unit continuity correction, let's draw a probability histogram around 45 first. Let's draw a probability histogram around 45 first. So assume 44 is here. Assume that's the probability when S is 44. 45 is here. Assume that's the probability when S is 45. 46 is here. Assume that's the probability when S is 46. And that's the probability when S is 47. And so on. We are looking for probability that S is greater than or equal to 45, which means S could be 45, 46, 47 until infinity. Here, X is a Poisson random variable with lambda equal to 40, which means lambda is sufficiently large. When lambda is sufficiently large, X tends to a normal approximation. S tends to a normal distribution. By central limit theorem, when lambda is sufficiently large, X tends to a normal distribution. In order to apply normal approximation, we try to approximate area under the curve over these bars. We try to approximate area under the curve over these bars. So here, the endpoint is the midpoint between 44 and 45. The endpoint is the midpoint between 44 and 45, which is 44.5. So X here tends to a normal distribution. We're looking for a probability that X is greater than 44.5. When lambda is sufficiently large, X tends to a normal distribution. And we are looking for a probability that X is greater than 44.5. Since X has a normal distribution, we can try to convert X to the standard normal distribution first, then use the table of the standard normal CDF to find the probabilities. So let's convert X to the standard normal distribution first. The formula for conversion is Z equal to X minus mu over sigma. So here we use 44.5 minus mu over sigma. Here mu is 40, sigma is radical 40. So we use X minus mu over sigma. Then use calculator. Round the answer to 2 decimal places. Use calculator. Round the answer to two decimal places. Here I get 0.71. Next, in order to use the table of the standard normal CDF, we must rewrite the probability in the form of probability Z is less or equal to some number, or probability that Z is less than some number. They both equal to phi of the number Z, the constant Z. They both equal to the phi of the constant Z. Here, probability that Z is greater than 0.71 can be rewritten as 1 minus probability that Z is less or equal to 0.71. That's 1 minus phi of 0.71. Then use the table of the standard normal CDF. Find phi of 0.71. 0.71 is here. I get 0.76115. 0.76115. Then subtract. I get 0.2385. In general, we want to answer to 4 decimal places. So it's approximately 0.2389. That's part B. That's the probability that at least 45 customers visit. That's the probability that at least 45 customers visit. Part C. In a given day, what's the probability that the number of visiting customers is between 30 and 50 exclusive Let's set down a problem first. For part C, we're looking for probability that S is between 30 and 50 exclusive. If we try to find this probability directly, we must compute f of 31 plus f of 32 plus plus f of 49. From f of 31 to f of 49, there are 18 terms. We must compute each term individually and then add them up. It's doable, but maybe too much work. In order to make the problem a little easier, we can use normal approximation. Here, x is a Poisson random variable with lambda equal to 40. We know that if lambda is more than 20, when we use normal approximation, it will be a good approximation. So let's use normal approximation here. Since x is a Poisson random variable, it's discrete. When we apply normal approximation, we need to use half-unit continuity correction. Let's apply half-unit continuity correction. In order to apply half-unit continuity correction, let's draw a probability histogram around 30 and 50 first. Let's draw a probability histogram around 30 and 50 first. Assume that the probability where S is 29. Assume that the probability where S is 30. Assume that the probability where S is 31. Assume that the probability where S is 49. Assume that the probability where S is 50. Assume that the probability where S is 51. And so on. We're looking for a probability that S is between 30 and 50 exclusive. That means we don't include 30, we don't include 50. So start from 31, 32, 33 until 48, 49. We don't include 30 and 50. Since x is a Poisson random variable with lambda equal to 40, which is sufficiently large. When lambda is sufficiently large, x tends to a normal distribution. When lambda is sufficiently large, by central limit theorem, x tends to a normal distribution. When we use normal approximation, we try to approximate area under the curve over these bars. So for these bars here, the left endpoint is the endpoint between 30 and 31, which is 30.5. The right endpoint is the midpoint between 49 and 50, which is 49.5. So if we use normal approximation with a continuity correction, we have probability that x is between 30.5 and 49.5. This x tends to a normal distribution. Since x has approximately normal distribution, we can convert x to the standard normal distribution, then use the table of standard normal CDF to find the probability. Let's convert x to the standard normal distribution first. The formula for conversion is z equal to x minus mu over sigma. So here we use 30.5 minus mu over sigma. Here, mu is 40, sigma is radical 40. So use 30.5 minus 40 over radical 40. For 49.5, do the same thing. Use 49.5 minus mu over sigma. Next, use calculator, find these two values, and round the answer to 2 decimal places. Here I get negative 1.50 and positive 1.50. In order to use the table of the standard normal CDF to find the probability, we try to rewrite the probability in the form of probability z is less or equal to some number, or probability z is less than some number. They both equal to phi of the number. So here, this probability can be rewritten as probability that z is less than 1.50 minus probability that z is less or equal to negative 1.50. That's phi of 1.50 minus phi of negative 1.50. Then use the table of the standard normal CDF to find the probabilities. In the table, 1.50 for 1.50, 1.5 is here. That's 1.50, 0.93319. That's phi of 1.50, 0.93319. Next, find phi of negative 1.50. Negative 1.5 is here, 0 is here. Phi of negative 1.50 is 0.06681. 0.06681. Then subtract. I get 0.86638. I get 0.86638. In general, we round the answer to 4 decimal places. Here I get 0.8664. That's the probability that the number of visiting customers is between 30 and 50. That's the answer to part C. Next example. In a train station, on average, there's a train arriving every 3 minutes during the rush hours. Rush hour means from 7 to 10 a.m. in weekday mornings. Assume arrivals of the trains are independent. Part A. In a given weekday morning, what's the probability that exactly 50 trains arrive in the train station during the rush hours? Part B. In a given weekday morning, what's the probability that no more than 55 trains arrive in the station during the rush hours? Part C. In a given weekday morning, what's the probability that the number of arriving trains in the station is between 45 and 70 inclusive? Let's set up a problem first. In this problem, we are looking for the number of arriving trains during the rush hours from 7 to 10 a.m. in weekday mornings. And we know that, on average, there's an arriving train in every 3 minutes. Since we know the average number of arriving trains, we can use Poisson distribution. Since we know the average number of arriving trains during a fixed time interval, we can use Poisson distribution. So let's set up a problem. Let the random variable x represent the number of arriving trains. During the rush hours. In your weekday morning. Then x has a Poisson distribution. X has a Poisson distribution. What's lambda here? During the rush hour, from 7 to 10 a.m., there are 3 hours. 3 hours means 180 minutes. We know that, on average, there's one train in every 3 minutes. How many trains do you expect to have in 180 minutes? From 7 to 10 a.m. means there are 3 hours. 3 hours is the same as 180 minutes. We are looking for the number of arriving trains on average from 7 to 10. Then solve an equation. If I cross multiply, 3 lambda equal to 180, lambda equal to 60. That means from 7 to 10 a.m. on average, we expect 60 arriving trains. So lambda is 60. Then next we can find expected value of x and the variance of x. In the earlier section, we know that expected value of x for Poisson distribution, expected value of x is the same as lambda, which is 60. And the variance of x is also lambda, that's 60. Then we know that mu of x is the same as expected value of x, they equal to 60. Sigma of x is square root of the variance of x, which is square root of 60. That's the setup of the problem. Now, based on the setup, let's answer the question. Part A. In a given weekday morning, what's the probability that exactly 50 trains arrive in the station during the rush hours? So for part A, we're looking for probability that x is 50. If I try to solve it directly using the probability function, I can try to find f of 50. Since x is a Poisson random variable with lambda equal to 60, its probability function f of x is e raised to negative lambda times lambda to the power of x over x factorial, with s equal to 0, 1, 2 until infinity. So for f of 50, we plug in 50 for x. I get e raised to negative 60 times 60 to the power of 50 over 50 factorial. Then use calculator. Round the answer to 4 decimal places. I get 0.0233. This is the exact answer. That's an actual probability without using approximation. This is the exact answer. That's the exact probability. That's the exact probability without using approximation. Now, if I try to use normal approximation, what do I get? Since x is a Poisson random variable with lambda equal to 60, we know that if lambda is more than 20, when we use normal approximation, it's a good approximation. So let's use normal approximation here. Since x is a discrete random variable, when we use normal approximation, we need to apply half-unit continuity correction. Since x is a discrete random variable, when we use normal approximation, we need to apply half-unit continuity correction. So let's apply half-unit continuity correction. If I apply half-unit continuity correction, for probability that x equal to 50, we go down by half unit. 50 minus half is 49.5. And then I go up by half unit. 50 plus half is 50.5. We know that when lambda is sufficiently large, x, this random variable x, tend to a normal distribution. Since x has approximately a normal distribution, we can convert x to the standard normal distribution first, then use the table of the standard normal CDF to find the probability. Let's convert x to z first. Let's convert x to the standard normal distribution first. The formula for conversion is z equal to x minus mu over sigma. Here mu is 60 and sigma is square root of 60. So we have 49.5 minus mu over sigma. Convert x to z. On the other side, we get 50.5 minus mu over sigma. Then calculate this expression using calculators. Round to 2 decimal places. Use calculator, round to 2 decimal places. I get negative 1.36 and negative 1.23. Next, in order to use the table of the standard normal CDF to find a probability, we try to rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of the number. They both equal to phi of this number. So here, this probability can be rewritten as probability that z is less than negative 1.23 minus probability that z is less or equal to negative 1.36. That's phi of negative 1.23 minus phi of negative 1.36. Now let's use the table of the standard normal CDF. In the table, phi of negative 1.23, 1.2 is here, 3 is here. I get 0.10935, 0.10935, 0.10935. Then for phi of negative 1.36, negative 1.3 is here, 6 is here. I get 0.08691, 0.08691. I get 0.08691. Then subtract. I get 0.02244. In general, for the final answer, we round to 4 decimal places. I get 0.224. That's an approximate probability. This is an approximate probability using normal approximation. You can see that it's very, very close to the actual answer. When lambda is sufficiently large, the answer is very, very close to the exact answer. That's a normal approximation. So that's a probability. That's a probability that exactly 50 trains arrive at the station during the rush hour. That's part A. Part B. In a given weekday morning, what's the probability that no more than 55 trains arrive at the station during the rush hours? No more than 55 trains means 55 or less. Means 55 or less. So let's set up a problem first. For part B, we're looking for a probability that x is less than or equal to 55. If we try to find a probability directly using the probability function f of x, then we need to compute f of 0 plus f of 1 plus f of 2 plus plus f of 55. We know that from f of 0 to f of 55, there are totally 56 terms. We need to compute each term individually and then add them up, find the sum. That's the probability that x is less or equal to 55. If we solve it in this way, it may be too much work. An easier way is we can try to use normal approximation. Since x is a Poisson random variable with lambda equal to 60, when we use normal approximation, it will be a good approximation. When lambda is more than 20, when we use normal approximation, it will be a good approximation. So let's use normal approximation. Since x is a discrete random variable, when we use normal approximation, we need to apply half-unit continuity correction. Let's apply half-unit continuity correction here. In order to apply half-unit continuity correction, let's draw the probability histogram around 55. Let's draw the probability histogram around 55. Suppose that's the probability where s is 53. And suppose that's the probability where s equals 54. Suppose natural probability y is equal to 55. Suppose natural probability y is equal to 56. And so on. We are looking for probability that x is less than or equal to 55. So start from 55. We are looking for all x below 55. We know that when lambda is sufficiently large, by central limit theorem, this Poisson random variable x tends to a normal distribution. When lambda is sufficiently large, x tends to a normal distribution. And when we use normal approximation, we're looking for probability under the curve over these bars. We're looking for probability under the curve over these bars. So for these bars here, the endpoint is the point between 54 and 56. So the endpoint here is 55.6, 55.5. The endpoint here is the midpoint between 54 and 56. So here is 55.5. So if we use normal approximation, x tends to a normal distribution. We're looking for probability that x is less than 55.5. Since x has an approximate normal distribution, we can try to convert x to the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. Let's first of all convert x to z, the standard normal distribution. The formula for conversion is z equal to x minus mu over sigma. Here, mu is 60, sigma is radical 60. So if I convert, I have z is less than 55.5 minus mu over sigma. Then calculate this using calculator. Round to 2 decimal places. Here I get z is less than negative 0.58. Then this is phi of negative 0.58. Probability that z is less than negative 0.58 is phi of negative 0.58. Then it's a table. Find phi of negative 0.58. Negative 0.5 is here. A is here. 0.08 is here. I get 0.28096. 0.28096. In general, for the final answer, round to 4 decimal places, I get 0.2810. That's the probability that no more than 55 trains arrive during the rush hours. That's the answer to part B. Part C. In a given weekday morning, what's the probability that the number of arriving trains in the station is between 45 and 70 inclusive? So let's set down a problem first. For part C, we're looking for probability that x is between 45 and 70 inclusive. If we try to find the probability directly using the probability function, we need to find f of 45 plus f of 46 plus until f of 70. From f of 45 to f of 70, there are 26 terms. We must compute each term individually and then add it up. If we solve it this way, it may be too much work. If we solve it this way, it may be too much work. So for this problem, let's try to use normal approximation. It may be a little easier. Since x is a Poisson random variable with lambda equal to 60, we know that if lambda is sufficiently large, if lambda is more than 20, when we use normal approximation, it will be a good approximation. Since x is a discrete random variable, when we apply normal approximation, we need to apply half-unit continuity correction. Since x is a discrete random variable, when we apply normal approximation, we need to apply half-unit continuity correction. In order to apply half-unit continuity correction, let's draw a histogram around 45 and 70 first. Let's draw a histogram around 45 and 70. Suppose that's the probability when s equal to 44. Suppose that's the probability when s equal to 45. Suppose that's the probability when s equal to 46. And continue on the other side. Suppose that's the probability when s equal to 69. Suppose that's the probability when s equal to 70. Suppose that's the probability when s equal to 71. We are looking for the probability that x is between 45 and 70 inclusive. So on the left side, I start from 45, then 46, everything in the middle, until 69 and 70. Since x is a Poisson random variable with lambda equal to 60, we know that when lambda is sufficiently large, x tends to a normal distribution by central limit theorem. When we use normal approximation, we try to find area under the curve overly sparse. We try to find area under the curve overly sparse. If we use normal approximation, we try to find area under the curve overly sparse. For this sparse here, the left endpoint is the midpoint between 44 and 45. So the left endpoint is 44.5. The right endpoint is the midpoint between 70 and 71. So the right endpoint here is 70.5. So when x tends to a normal distribution, x is between 44.5 and 70.5. Since x has an approximate normal distribution, we can convert x to the standard normal distribution. Then use the table of the standard normal CDF to find the probability. Let's first of all convert x to the standard normal distribution. The formula for conversion is z equal to x minus mu over sigma. So here we use (44.5) minus mu. Mu is 60 over sigma. Sigma is square root of 60. Convert x to z. On the other side, on the right side, do the same thing. Take 70.5 minus mu over sigma. Sigma is radical 60. Then compute this. Use calculator, round to 2 decimal places. Here I get negative 2.00 and 1.36. Then, in order to use the table of the standard normal CDF to find the probability, we must rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of the number, phi of the given number. They both equal to phi of the given number. Here, this probability can be written as probability that z is less than 1.36 minus probability that z is less or equal to negative 2.00. That's phi of 1.36 minus phi of negative 2.00. Next, a table. Phi of 1.36. 1.3 is here. 0.06 is here. I get 0.91309. 0.91309. Minus phi of negative 2.00. Negative 2 is here. 0.00 is here. I get 0.02275. 0.02275. .02275. Then subtract. I get .A9034. In general, for the final answer, round the answer to 4 decimal places. I get .A903. I get .A903. That's a property that the number of arriving trains is between 45 and 70 during the rush hours. That's the answer to part C.